The universe is not a random sea of stars. It is a vast, geometric tapestry, a hidden architecture that controls everything from the birth of galaxies to the fate of the cosmos itself. For centuries, the night sky looked like chaos, but we now know a precise cosmic web connects it all, a structure of immense filaments, dense clusters, and empty voids. This is the hidden geometry shaping the cosmic web of galaxies. By the end of this exploration, you will understand the invisible skeleton of reality and see the universe in an entirely new way. What force wrote this blueprint into the fabric of space, and could its geometric rules reveal secrets about our own existence? What does this grand design make you wonder about your place in the cosmos? But to see this geometry, you must first step back, way back. Picture the entire observable universe not as a collection of points of light, but as a single, colossal structure. It resembles a cosmic sponge, or perhaps the delicate neural network of a brain on a scale beyond comprehension. This is the cosmic web, the largest single thing we have ever identified. Its threads are filaments of dark matter and glowing gas, shimmering across billions of light years. Along these threads, galaxies gather like beads on a string. Between them stretch the voids, immense regions of near-total emptiness so vast they could swallow thousands of galaxies without a trace. For most of human history, we saw the cosmos as a roughly even sprinkling of stars. The revelation of this web, this immense architecture, was a revolution in thought. It told us the universe has a skeleton, a hidden framework that organizes everything. This framework is built from three core components. First, the dense clusters, where thousands of galaxies swarm in a frenzied gravitational dance. Second, the filaments themselves, the long, winding cosmic highways that connect these dense urban hubs. And third, the voids, those profound deserts of space that make up the overwhelming majority of the universe's volume. This entire breathtaking structure did not emerge from randomness. Its blueprint was written in the first moments of time, imprinted as tiny quantum ripples in the newborn cosmos. Over billions of years, gravity acted as a slow, relentless sculptor, amplifying those ripples into the majestic web we see today. To understand the hidden geometry shaping reality, we must first appreciate this canvas. The web sets the stage, dictating where galaxies can form and how they will grow. It is the ultimate expression of a universe governed by rules, a puzzle waiting for its mathematical key. That magnificent visible structure rests upon a ghost. All those glowing filaments and brilliant clusters are merely decorations draped over an invisible framework, a cosmic skeleton we can never see directly. This is the realm of dark matter, the silent architect of the universe. Think of it as the steel girders inside a towering skyscraper. You admire the glass, the shape, the lights within, but the entire edifice is held aloft by a hidden armature you never perceive. Dark matter is that armature for the cosmos. It is a form of matter that does not emit, absorb, or reflect any light. It is utterly dark, interacting with the familiar world of atoms and stars through gravity alone. Yet despite its ghostly nature, it is not a minor component. For every single particle of the ordinary matter that makes up planets, stars, and our own bodies, there is roughly 5 times more dark matter. It constitutes the overwhelming majority of the universe's mass, meaning the gravity that shapes the cosmos is primarily the gravity of something we cannot see. This invisible substance is the master sculptor. In the aftermath of the Big Bang, the universe was a nearly smooth soup of particles, but it was not perfectly smooth. Tiny quantum ripples existed, minute variations in density. Dark matter, responsive only to gravity, began to respond to these ripples first. Its particles started to gather, slowly, over hundreds of millions of years into an immense, delicate web of tendrils and knots under their own gravitational attraction. This process created a gravitational landscape, a map of hills and valleys made purely from the pull of dark matter. Ordinary matter, the gas that would become galaxies, was simply a passenger. As the universe expanded and cooled, this gas flowed along the gravitational contours laid down by the dark web, sliding into the deepest valleys and collecting along the highest ridges. Where dark matter formed a dense knot, galaxies would later swarm into a brilliant cluster. Where it stretched into a long filament, galaxies would line up like pearls on a string. The luminous universe we observe is just tracing the outline of this far grander, darker architecture. Supercomputer simulations of cosmic evolution paint this story with stunning clarity. They begin with a smooth distribution of dark matter particles and the laws of physics, then let gravity work over billions of simulated years. The result is not a random scatter. It is an intricate cosmic filigree, a three-dimensional lace of dark matter filaments intersecting at dense nodes. When scientists overlay the observed positions of millions of real galaxies onto these simulations, the match is breathtaking. The galaxies sit precisely along the simulated dark matter threads, clustering at the intersections. It is as if we predicted the location of every major city on Earth by first mapping the mountain ranges and river valleys. Without dark matter's gravitational blueprint, the primordial gas would have remained diffuse, never clumping strongly enough to ignite the first stars. There would be no web, no grand clusters, no galaxies, and certainly no planets or life. The geometry we seek begins in the dark, with an unseen framework that dictates where light itself is allowed to shine. This realization shifts our search. If dark matter draws the blueprint, then gravity is the pen. So how does this force, acting on an invisible canvas, create such precise and universal shapes? Gravity is the patient chisel that carved the cosmos from a formless fog. In the beginning, the universe was a near-perfect soup, a sea of particles so uniform you could travel for millions of light years and see almost no difference from one region to the next. Almost hidden within that smoothness were the faintest of ripples, tiny variations in density no larger than 1 part in 100,000. Think of the surface of a vast, calm ocean, but with imperfections so slight they are mere whispers against the water. These whispers held the entire future. Gravity heard them. It is an irresistible force of attraction, and it began its work with infinite patience. Where there was just a little more matter, gravity's pull was slightly stronger. That stronger pull attracted even more matter from the surroundings, making the dense spot denser still. Over millions, then billions of years, this simple feedback loop, this process of gravitational instability, transformed a whisper into a shout. Those minuscule over-densities became the seeds of everything. They grew into the mighty nodes where galaxy clusters now swarm. The matter flowing into these seeds did not arrive from all directions equally, however. It streamed in along specific paths, like rainwater finding the grooves in a pane of glass. These streams of infalling matter became the long, winding filaments of the cosmic web. Meanwhile, the regions that started with just a little less material faced the opposite fate. As gravity pulled matter toward the growing seeds, these under-dense regions were slowly drained. They expanded not because they were pushing outward, but because they were being left behind. These became the cosmic voids, the great deserts of space that make up most of the universe's volume. So the web's geometry is not static, it is a snapshot of an eternal flow. Gravity is still sculpting today. Galaxies are not fixed ornaments on this structure, they are travelers. They slide along the dark matter filaments, following the gravitational currents toward the dense clusters at the intersections, in a migration that will continue for eons. This reveals a profound truth about our universe. Its grand design is not a frozen blueprint, but a dynamic and ongoing construction project. The shapes we see, the filaments and voids, are the direct result of a 13.8 billion year-long competition. On one side, gravity's relentless pull seeks to clump everything together. On the other, the expansion of the universe works to pull everything apart. The cosmic web is the intricate pattern that emerges where these two titanic forces reach a temporary, beautiful stalemate. This leads us to a pivotal question. If gravity is the sculptor and dark matter is the clay, what exactly determined the pattern of those initial ripples? What hand wrote the first subtle variations into the smooth canvas of the newborn cosmos, setting this entire majestic chain reaction into motion? These vast, silent chambers hold the key to the universe's shape. If filaments and clusters are the bright threads and knots of the cosmic web, then voids are the dark, geometric spaces in between. They are not simply accidents of emptiness, but actively sculpted regions that define the web's very architecture. Picture a cosmic foam where each bubble is a void, a spherical or slightly stretched chamber so immense it could contain thousands of galaxies, yet holds almost none. These are the low-density deserts of the cosmos, making up the overwhelming majority of the universe's volume. Their existence is a direct result of gravity's work. As matter flowed for billions of years into the growing filaments and clusters, these regions were gradually evacuated, leaving behind profound pockets of near-nothingness. The geometry of these voids is not random. Their shapes, their sizes, and how they are distributed across space are like cosmic fingerprints. They encode vital information about the fundamental forces at play, particularly the mysterious influence of dark energy, which drives the universe's accelerating expansion. Think of the universe as an expanding loaf of raisin bread. The raisins are galaxy clusters. The voids are the expanding spaces of dough between them. By measuring the precise size and growth of these empty chambers over cosmic time, scientists can gauge the push of dark energy against the pull of gravity. Even more fascinating, voids are not completely barren. They possess their own subtle structure. Most have faint, surrounding walls where a few scattered galaxies linger, and deep within some voids drift isolated void galaxies, rare stellar islands that for some reason never joined the great migration to the filaments. Light itself is affected by these empty chambers. When light from a distant galaxy travels through a void, the lack of gravitational pull in that region causes the light's path to bend ever so slightly, a phenomenon that subtly alters what we see. By studying this effect, cosmologists can test the very laws of gravity on the largest scales. So these great cosmic absences are not passive background. They are active participants in the cosmic drama, their empty geometries defining the positive spaces where all luminous matter resides. To understand the full design, we must now turn from these expansive deserts to the dense, brilliant cities they surround. While voids define the silent chambers of the cosmos, the filaments are its vibrant, living arteries. These are the luminous rivers of the cosmic web, colossal bridges of dark matter and hot gas that stretch for millions of light years, connecting the dense clusters like cities linked by a network of superhighways. Their scale is almost impossible to grasp. A single filament can be longer than the distance between our Milky Way and the Andromeda Galaxy 100 times over, yet it may be only a fraction of that in width, making it a thread of astonishing delicacy woven across the void. This is where the universe conducts its most dramatic flows of matter and energy. Galaxies do not simply float in empty space, they are carried along these currents. Picture a string of brilliant pearls, each one a galaxy, sliding along a glowing wire in the darkness. They are in motion, following the gravitational pull of the filament itself, migrating slowly but inevitably toward the massive clusters where these cosmic roads intersect. The geometry of these filaments is not simple or neat. They are not straight lines drawn across the universe. Instead, they curve and branch in complex, beautiful patterns, tracing the contours of the underlying dark matter skeleton like rivers following the slope of a hidden landscape. Their winding paths tell the story of gravity's patient work, of flows and mergers that have been ongoing for billions of years. These structures are the primary channels for cosmic evolution. Vast reservoirs of hydrogen gas, the raw fuel for new stars, stream along these filaments. When this river of gas flows into a waiting galaxy cluster, it can trigger bursts of star formation, lighting up the galactic metropolis with newborn suns. The filaments themselves can sometimes glow faintly with the light of this hot, diffuse gas, a subtle aurora on a universal scale. Our most detailed maps of the universe, like those from the Sloan Digital Sky Survey, reveal this intricate architecture in stunning detail. By plotting the positions of millions of galaxies, the ghostly outline of the filamentary web emerges from the data. We see the knots, the strings, the great empty bubbles in between. It is a cosmic cartography that shows us not just where things are, but how they are moving and how they are connected. This grand design points our attention toward the powerful, crowded places where these filaments meet. If filaments are the highways, then their intersections are the ultimate cosmic destinations. What happens in these dense, turbulent crossroads where the universe's great flows converge? Where the great filaments of the cosmic web converge, they build cities of unimaginable scale. These are the galaxy clusters, the dense, luminous metropolises that anchor the entire universal network. If a filament is a cosmic highway, a cluster is the vast, glittering megalopolis at its end, a gravitational sink where thousands of galaxies are gathered in a perpetual, swirling dance. They are not mere collections of stars, but the universe's most massive structures held together by gravity itself, containing not just galaxies but oceans of gas hotter than the core of any star, all shrouded within an immense, invisible cloak of dark matter. The geometry here is one of profound density and power. These clusters form at the deepest intersections of the dark matter skeleton, where gravitational wells are so strong they pull matter in from all directions for billions of years. The hot gas trapped within these wells glows in X-rays, a seething, multimillion-degree atmosphere that tells us about the cluster's immense mass and violent history. It is within these extreme environments that the hidden components of our universe become impossible to ignore. The sheer amount of gravity required to hold such a fast-moving, hot system together far exceeds what we can account for from the visible galaxies and gas alone. This missing mass is the signature of dark matter, its presence felt most strongly in these crowded hubs. By studying how clusters bend the light from galaxies behind them, an effect called gravitational lensing, we can literally map the distribution of this invisible substance, tracing the shape of the gravitational well that defines the cluster's core. The arrangement of these clusters across the cosmos is not haphazard. They sit at specific nodes within the web, and the distances between them, their alignments, and how they have grown over time form a precise record. This record encodes the universe's expansion history and the push of dark energy. Think of the cosmic web as a three-dimensional grid with clusters at the major intersection points. Measuring the scale of this grid at different epochs of cosmic time allows scientists to see how the push of dark energy has been stretching the very fabric of the structure. So these brilliant, chaotic cities are more than just endpoints, they are fundamental anchors. Their positions define the web's architecture, and their properties help us read the cosmic ledger, revealing the balance of forces that has shaped everything. To see the full majesty of this design, we must now step back once more, to view not just the cities or the highways, but the breathtaking symmetry of the entire pattern. The universe's grand design was not drawn at random, but written in code during its very first moments. To understand the hidden geometry we see today, we must travel back to a time before stars, before atoms, before even the simplest particles had formed. In the first unimaginably tiny fraction of a second after the Big Bang, the entire cosmos underwent a period of hyper-accelerated expansion called inflation. Space itself ballooned faster than the speed of light, stretching a subatomic volume to something larger than our observable universe in less than a blink. This violent growth spurt did something profound to the fabric of reality. At the quantum level, empty space is not truly empty. It is a seething sea of virtual particles flickering in and out of existence, a foam of fleeting energy fluctuations. Inflation took these quantum jitters, these microscopic tremors in the newborn cosmos, and stretched them to astronomical proportions. A fluctuation smaller than a single proton one moment could, an instant later, be inflated to a scale spanning thousands of light years. This process imprinted a specific pattern of slightly denser and slightly less dense regions onto the entire universe. Think of it like stretching a rubber sheet that has a fine, random texture. As you pull it, the tiny bumps and dimples become large, gentle hills and valleys. Those hills and valleys were the seeds of everything to come. They represented the faintest possible variations in density, mere parts in 100,000, but they were the only blueprint gravity would ever need. For hundreds of thousands of years, the universe remained too hot and dense for light to travel freely. It was an opaque, glowing fog. Then, as it expanded and cooled, it finally became transparent. The light released in that moment has been traveling to us ever since, carrying with it a perfect snapshot of that infant cosmos. We see it today as the cosmic microwave background, a faint, cold glow that permeates all of space. This afterglow is not perfectly uniform. When we map it with satellites like Planck, we see a mottled pattern of minute hot and cold spots. These spots are not random noise. They are the direct, fossilized imprint of those primordial quantum hills and valleys, the cosmic blueprint frozen in time. The precise geometry of these spots, their angular sizes, and how they correlate with one another across the sky is a mathematical treasure map. It tells us with astonishing precision what the initial conditions of the universe were. Cosmologists can take this pattern, feed it into the known laws of physics and gravity, and run the cosmic clock forward in supercomputer simulations. The result is always the same. Those tiny temperature variations evolve over billions of simulated years into the exact kind of cosmic web we observe, complete with its filaments, clusters, and vast voids. The cold spots in the ancient afterglow often become the seeds of today's great galaxy clusters, while the warmer regions hint at the future locations of the empty voids. This provides a breathtakingly direct link. The subtle patterns we see in the afterglow of creation are the very same patterns that dictated where our Milky Way galaxy would one day form. The geometry was set from the start, a signature written in the first instant and revealed in the faint whisper of microwave light that fills the sky. But how do we translate that whisper, that mottled map of hot and cold, into a precise prediction for a three-dimensional web of galaxies? The answer lies in a language of angles, correlations, and a powerful mathematical lens. The blueprint for the cosmos is written in a mathematical language of angles and correlations. To translate the mottled map of the ancient afterglow into the three-dimensional web we see today, scientists use a powerful tool called the correlation function. In essence, this is a cosmic census that asks a simple, profound question. If you find a galaxy at a random point in space, what are the odds of finding another galaxy at a specific distance from it? The answer is not random. Galaxies are far more likely to be found relatively close to one another, strung along filaments, and much less likely to be found isolated in the deep voids. By measuring these probabilities across vast distances, the correlation function reveals the hidden skeleton. It quantifies the clustering, the tendency of matter to gather with its own kind, and it shows how this clustering changes with scale. The pattern that emerges from this cosmic statistics is not smooth or featureless. It reveals a distinct, characteristic scale imprinted by those primordial sound waves in the early universe, a preferred distance at which galaxies like to cluster. This signature is a direct prediction from the physics of the infant cosmos, and finding it in the modern galaxy distribution was a triumphant confirmation of our entire cosmological model. It proves the ancient blueprint and the modern structure are one and the same story, told 13.8 billion years apart. This statistical signature, however, leads to an even deeper geometric mystery. If you zoom in or out on this cosmic pattern, does it ever truly look the same? This hidden geometry reveals itself not just in distances, but in connections. To understand the cosmic web as a living network, we must explore its topology, the study of shapes and how they are connected. Think of a coffee mug and a donut. To a topologist, they are the same shape because each has exactly one hole. You could, in theory, mold one into the other without cutting or tearing, just by stretching and bending. This focus on connectivity over exact measurement gives us a profound new way to see the universe's architecture. We move beyond asking how far apart two galaxies are, and instead ask, are they linked by the same filament? Is this void a simple bubble, or does it connect to others through hidden tunnels? Does the entire cosmic structure contain loops like the holes in a sponge, or is it more like a simple stack of separated layers? By analyzing the immense maps from galaxy surveys, scientists can compute mathematical descriptors called topological invariants. One key measure is the genus, which essentially counts the number of donut-like holes in the cosmic structure at different density levels. Imagine taking a slice through the universe and looking at the contours where matter is concentrated. A high genus number means a complex, interconnected landscape full of loops and tunnels, like an intricate lace or a sponge. A low genus number suggests a simpler world of isolated hills and separated basins. What do we find when we apply this to the real cosmos? The universe displays a remarkably sponge-like topology. It is richly interconnected, with filaments looping back to form cosmic highways that link clusters in a complex, three-dimensional tangle. This is not a static fact. It is a dynamic record. As gravity works over billions of years, it continuously modifies this connectivity. Early in the universe's history, the topology was likely simpler. But as matter flowed along the dark matter skeleton, it carved out these tunnels and loops, weaving the isolated denser regions into the single, vast web we see today. This topological perspective offers a uniquely robust test for our theories. Because it cares about connections rather than precise scales, it remains reliable even when our distance measurements have some uncertainty. If our cosmological models are correct, they should predict not just the sizes of clusters, but the specific, sponge-like connectivity of the entire network. The fact that they do is a stunning confirmation. It tells us that the universe is not just a collection of objects, but a single, coherent geometric entity, shaped by rules that we are slowly deciphering. To truly witness this connectivity in action, we must turn to the most powerful tools of modern cosmology, the supercomputer simulations that bring the invisible architecture to life. The universe's hidden architecture comes to life not just in our telescopes, but inside our most powerful supercomputers. To truly see how the cosmic web grew from a smooth whisper into a majestic structure, scientists build entire virtual universes from scratch. These are known as n-body simulations, and they are among the most ambitious calculations ever attempted. The principle is deceptively simple, yet the scale is staggering. You begin with a virtual box representing a vast chunk of space. You populate it with billions, even trillions of simulated particles, each one standing in for a parcel of dark matter. You give these particles the initial conditions drawn from that ancient cosmic microwave background map, the faint hills and valleys from the dawn of time. Then you press start. The simulation runs the laws of physics, primarily gravity, forward across billions of virtual years. Every single particle feels the gravitational tug of every other particle, a dance of unimaginable complexity choreographed by pure mathematics. What emerges from this digital primordial soup is nothing short of breathtaking. Over eons of simulated time, the particles begin to move. They are not moving randomly. They flow along the invisible contours of their own collective gravity, streaming into the denser regions and fleeing the emptier ones. Slowly, a pattern condenses out of the chaos. Filaments of connected particles stretch across the void. Vast spherical bubbles of emptiness grow and merge. At the intersections of the filaments, dense knots of particles form, the seeds of future galaxy clusters. Watching this process unfold in a supercomputer visualization is like having a time machine for the cosmos. You witness the web being woven in fast forward, seeing the precise moment when a delicate bridge forms between two growing clusters, or when a void clears itself of matter entirely. These visualizations are not artistic interpretations, they are direct mathematical predictions. They show us what our theories say should happen, given the starting conditions and the laws we believe govern the universe. The most famous of these digital universes, like the Millennium Run or the more recent Illustris TNG project, have become foundational to modern cosmology. They allow researchers to perform experiments that would be impossible in reality. What happens if we change the nature of dark matter? What if gravity behaves slightly differently on cosmic scales? You can alter the rules in the simulation, run it again, and see what kind of cosmic web emerges. Does it still produce the delicate, sponge-like filamentary structure we observe, or does it create something else entirely? A universe of isolated blobs or a featureless haze? By comparing the intricate geometry of these simulated webs to the maps we create from galaxy surveys, we ground our most abstract theories in virtual experimentation. When the simulated web matches the observed one in exquisite detail, it gives us profound confidence that we are on the right track, that we understand the hidden forces that shaped everything. These silicon universes reveal a final, humbling truth. The majestic cosmic web we see through our telescopes was not a guaranteed outcome. It is the specific, beautiful result of a precise recipe, written in the first instant and baked by gravity over all of time. The universe holds a whisper from its infancy, a frozen echo that gives us a perfect measuring stick. This is the story of Baryon acoustic oscillations, a mouthful of a term for one of cosmology's most elegant tools. To understand it, we must return to that hot, dense early universe, a seething plasma of light and matter. In that primordial soup, photons of light and the particles of ordinary matter, called baryons, were locked in a constant, furious dance. They were so tightly coupled that they behaved almost as a single fluid, and in any fluid, disturbances create waves. In this cosmic fluid, the disturbances were those same quantum ripples from inflation, and they created sound waves. Real physical pressure waves that propagated outward from every slightly denser region, like ripples from a stone dropped in a pond. For nearly 400,000 years, these sound waves raced through the plasma, expanding in spherical shells. But then, the universe crossed a critical threshold. It expanded and cooled enough for atoms to form. Suddenly, the photons were set free, streaming across the cosmos as the cosmic microwave background. The ordinary matter particles, now neutral atoms, were left behind, and crucially, the sound waves stopped in their tracks. They froze. Imagine a pond of water instantly turning to solid ice, capturing the ripples at a precise moment in time. That is what happened to these cosmic sound waves. Each dense seed was left surrounded by a faint, spherical shell of matter, a fossilized echo of that primordial sound. This shell had a very specific radius. The distance sound could travel in that 400,000-year period before the universe became transparent. That distance became a fundamental yardstick imprinted onto the cosmos. Today, billions of years later, we can still detect that signature. When we map the positions of millions of galaxies and perform those statistical correlation studies, we find a subtle but unmistakable signal. There is a slight but significant excess of galaxy pairs separated by a specific, enormous distance. That distance translates to about 500 million light-years. It is the grown-up, stretched version of that original frozen sound wave, expanded by the universe's own growth. This Baryon acoustic oscillation scale is our cosmic standard ruler. Because we know its original, true size from the physics of the early universe, we can use it to measure how much the universe has stretched since then. It works like this. We look at a galaxy survey from a relatively nearby volume of space and measure the apparent size of this standard ruler. Then, we look at a survey of galaxies much farther away, and thus from much earlier in cosmic time, and measure the ruler's apparent size there. By comparing the two, we can see exactly how the expansion of space has stretched the ruler over billions of years. This gives us a direct, precise history of the universe's expansion. The power of this geometric tool is immense. It allows us to probe the very shape of space on the largest scales. Is space flat like a sheet of paper? Is it positively curved like the surface of a sphere where parallel lines eventually meet? Or is it negatively curved like a saddle where they diverge? The apparent size of our standard ruler in different directions tells us, so far, every measurement points to a flat universe, a profound geometric fact with deep implications. Most importantly, tracking how the expansion rate has changed over time directly reveals the influence of dark energy. The ruler shows us how the stretching of space accelerated, pinning down the properties of this mysterious force that dictates the cosmos's ultimate fate. So that faint statistical preference for a certain galaxy separation is far more than a curious pattern. It is the ghost of a sound wave from the dawn of time, a frozen echo we use to measure the geometry of everything. These frozen echoes from the dawn of time give us a ruler, but to draw the map, we need to locate millions of galaxies in three-dimensional space. How do we actually chart the invisible architecture of the cosmic web? The key is not just seeing where a galaxy lies in the sky, but knowing how far away it is. That crucial third dimension comes from a phenomenon called redshift. As the universe expands, it stretches the very fabric of space, and the light traveling through that space gets stretched along with it. For light, stretching means shifting toward the red end of the spectrum. The farther away a galaxy is, the longer its light has been traveling, and the more it has been stretched by the expanding cosmos. By carefully measuring this redshift in a galaxy's light, astronomers can calculate its distance. This turns a flat picture of the sky into a deep, three-dimensional atlas of the universe. This is the monumental work of projects like the Sloan Digital Sky Survey. For over 2 decades, this ambitious project has used a dedicated telescope to systematically scan the heavens, not just taking pictures, but capturing the spectra of millions of celestial objects. Each spectrum is like a barcode, revealing the chemical fingerprint of a galaxy and, critically, its redshift. By processing this ocean of data, scientists can plot each galaxy in a vast cosmic coordinate system. When you plot millions of these points, the hidden architecture suddenly emerges from the noise. What looked like a random scatter resolves into the delicate tendrils of filaments, the sprawling empty spheres of voids, and the dense, glittering knots of galaxy clusters. These maps are the direct observational proof of the web, the real-world counterpart to the supercomputer simulations. They show us the geometry is not just a theoretical idea, it is the actual skeleton of our universe. Now, a new generation of instruments is taking this cartography to a breathtaking scale. The Dark Energy Spectroscopic Instrument, known as DESI, is currently undertaking one of the most ambitious surveys ever conceived. Mounted on a telescope in Arizona, DESI can capture the spectra of 5,000 galaxies at a single time, night after night. Its goal is to map the three-dimensional positions of tens of millions of galaxies and quasars, reaching back across 11 billion years of cosmic time. Each new survey adds staggering depth and clarity to our picture. With this immense statistical power, scientists can do more than just see the web. They can measure its geometry with precision. They can trace the subtle flow of galaxies as they drift along the gravitational currents of filaments, like watching leaves carried on a river. They can probe the intricate relationship between the glowing galaxies we see and the invisible dark matter scaffold that holds them in place. This empirical mapping is the crucial bridge between theory and observation. The simulations give us a universe as it could be, based on our physical laws. The Redshift Surveys show us the universe as it truly is. When we lay one over the other, the match is not just close, it is profoundly validating. It tells us our understanding of cosmic evolution, from those first quantum ripples to the grand web of today, is fundamentally correct. Yet, as our maps grow more detailed, they also reveal new puzzles. The geometry we see holds clues to forces we still do not fully understand, suggesting the cosmic web might be more than just a structure. It could be a cosmic clock recording the passage of time itself. The cosmic web is not a finished tapestry, but a canvas still being stretched. As our maps reach deeper into time, they reveal a subtle, relentless change in the geometry itself. This change is driven by a force that now dominates the cosmos: dark energy. Think of dark energy as a kind of cosmic tension, an inherent property of empty space that causes the universe's expansion not just to continue, but to accelerate. It is the ultimate opponent to gravity's gathering pull. For billions of years, gravity was the master sculptor, patiently pulling matter into filaments and clusters. But as the universe grew older and more diffuse, the influence of dark energy began to win out. Its effect on the web's architecture is profound and geometric. Imagine drawing a delicate pattern of interconnected lines on a rubber sheet, then slowly but firmly pulling the edges of that sheet in all directions. The lines themselves do not break, but they become thinner, more stretched. The empty spaces between them grow wider. This is what dark energy does to the cosmic web. It stretches the very fabric of space, working against gravity's attempts to pull matter together. As the acceleration increases over cosmic time, it becomes harder and harder for new filaments to condense from the primordial gas. The formation of new, massive galaxy clusters is effectively suppressed. Existing filaments, those great luminous highways, become more tenuous and diffuse as the galaxies within them are carried farther apart by the expanding space between them. The great voids, already vast, expand even faster, becoming ever more empty. In this way, the geometry of the web encodes the entire history of this cosmic tug of war. It is a dynamic fossil record. By measuring how the web's structure changes across different epochs, scientists can read this record. They look at the characteristic sizes of voids billions of years ago compared to voids today. They measure the typical thickness and connectivity of filaments in the ancient universe versus the modern one. Each of these geometric metrics tells a story about the strength and nature of dark energy's push. The web becomes more than a structure. It transforms into a precision diagnostic tool. The way its geometry has been stretched and frozen over time allows cosmologists to measure the properties of this mysterious dominant force. This turns our understanding of the cosmos into a deeply historical science. We are not just looking at a static shape, we are watching a slow-motion film of a battle between two fundamental aspects of reality, with the evolving web as our only visual evidence. The ultimate fate of this expansion, and thus the long-term future of the web itself, hinges on what these geometric clues reveal. If dark energy continues its relentless acceleration, the distant future holds a profoundly lonely geometry, one of isolated islands separated by an ever-widening abyss. Galaxies are not stationary points of light, they are travelers on a grand journey. Each one is caught in a vast, slow-motion river, a cosmic flow dictated by the hidden geometry of the web. These are not random wanderings, but coherent streams where thousands of galaxies move together, like leaves caught in the same current, hurtling through the void at speeds exceeding 1,000,000 kilometers per hour. Their destination is always the same, the deep gravitational wells where filaments intersect and galaxy clusters swell. This motion is the web's pulse, a direct testament to its dynamic, living nature. To understand it, picture rainwater on a mountain. A single droplet does not choose its path. It simply follows the slope of the land, flowing into gullies, merging into streams, and finally pooling in the valley below. The mountain's topography is invisible from a distance, but by watching the water's flow, you can map every ridge and channel. In the cosmos, the galaxies are the water, and the invisible topography is sculpted from dark matter. By measuring not just where a galaxy is, but how it is moving, astronomers can reverse engineer the shape of the entire gravitational landscape. This requires extraordinarily precise cosmic cartography. Scientists must know a galaxy's true distance independently of its motion-induced redshift, a difficult task that relies on certain types of stars or supernova as standard candles. Comparing this true distance to the galaxy's observed redshift, which is stretched by both cosmic expansion and its own peculiar velocity, reveals its actual speed and direction through space. When this is done for thousands of galaxies in our cosmic neighborhood, a stunning picture emerges. We see the entire local sheet of galaxies, including our own Milky Way, being pulled in a specific direction. We are part of an immense flow, streaming toward a distant, massive concentration of matter known as the Great Attractor, a region obscured by the dust of our own galaxy's plane. Beyond that, an even greater pull comes from the Shapley Supercluster, the most massive concentration of matter in our nearby universe. These flows allow us to weigh these colossal structures in a way light alone never could. By calculating how fast galaxies are being pulled toward an overdensity, we can calculate the total mass responsible for that pull, revealing the otherwise invisible dark matter scaffolding that binds the supercluster together. It is a form of cosmic-scale archaeology, using motion to uncover buried structure. These reconstructed velocity maps are transforming our understanding of our local cosmic address. They show our place within the flows not as a central reference point, but as a participant in a universal migration that has been ongoing for billions of years. Every galaxy we see is telling us through its motion where the mass is. This turns the cosmos into a dynamic sculpture, where the present arrangement is just a single frame in a film of perpetual gravitational evolution. The geometry is not just the shape of things, but the shape of their movement, a choreography written by gravity and performed across all of time. This grand flow of galaxies has a destination, and we are traveling toward it. Our Milky Way galaxy is not a stationary island in space. It is a ship caught in a powerful current, part of a vast migration of thousands of galaxies all moving in concert. This motion reveals our true address within the cosmic architecture. We are being pulled toward a mysterious, hidden region of immense gravity known as the Great Attractor. It lies in the direction of the southern constellations Norma and Centaurus, but its core is veiled from our direct view by the thick dust and stars of our own galaxy's central plane. For decades, this was a profound cosmic mystery, a shadowy gravitational giant we could sense but not see. What we could measure was its immense influence. By tracking the peculiar motions of galaxies around us, astronomers mapped a colossal flow. Everything in our local volume of space, across hundreds of millions of light years, is streaming toward this single point. The sheer scale of this motion tells us the Great Attractor is not a single object, but a massive concentration of mass, a deep knot in the cosmic web where multiple filaments converge. This gravitational anchor defines our home supercluster. We now know it as Laniakea, a Hawaiian word meaning immense heaven. Laniakea is not a simple sphere of galaxies. It is a sprawling, filamentary continent in the web. Picture a great cosmic watershed. The Great Attractor sits at its lowest gravitational point, and all the galaxies within Laniakea, including our Milky Way, are like water droplets flowing down the slopes of this invisible terrain toward that central basin. Our position within this structure is humbling and specific. We reside on the outskirts of one of Laniakea's major filaments, a galactic suburb rather than a downtown core. We are on the move, traveling along this filamentary arm toward the crowded intersection ahead. This intimate perspective transforms the cosmic web from an abstract concept into a personal reality. The same gravitational forces that sculpted the universe over billions of years are actively guiding the path of our own galaxy right now. Our fate is tied to these larger architectural flows. In time, the Milky Way, along with our entire local group of galaxies, will continue this journey, eventually merging with the vast assembly of galaxies in the Great Attractor region billions of years from now. This raises a profound question about symmetry. Is our place in the web unique, or is every galaxy cluster, every supercluster, shaped by similar dominant attractors? The search for other such massive gravitational anchors across the cosmos helps us test whether the web's structure is evenly balanced or lopsided, offering another clue to the initial conditions from which all this grandeur grew. The universe presents us with a beautiful paradox, a delicate balance between order and anomaly. On the grandest scales, the cosmic web appears statistically uniform, a principle known as isotropy. This means if you were to take a sufficiently large chunk of the cosmos, it would look roughly the same in every direction, with the same density of filaments, clusters, and voids. This large-scale symmetry is a cornerstone of modern cosmology, a direct prediction from the smooth, uniform conditions set by inflation. It tells us that no single location in the universe is special or central, a humbling and democratic view of reality. This uniformity is what allows us to use the web as a reliable measuring stick, confident that the rules of physics we deduce in our corner apply everywhere else. Yet when we peer into the data with exquisite precision, whispers of something else emerge. Subtle hints suggest the tapestry might not be perfectly woven. One of the most intriguing puzzles is known informally as the axis of evil. This is not a malevolent force, but a curious statistical alignment found in the cosmic microwave background, that ancient snapshot of the infant universe. Certain patterns in that afterglow, the hot and cold spots, appear to be aligned along a particular plane in the sky, more than our standard models predict. It is as if the universe's first breath had a faint preferred direction, a whisper of a tilt written into the fabric of space at the very beginning. Then there are the large-scale bulk flows, the motions of entire superclusters that seem to indicate a gravitational pull from structures even more immense than those we have mapped. These flows suggest the distribution of mass on the very largest scales might not be perfectly even, that there might be a cosmic watershed vaster than Laniakea, pulling on everything within its reach. The question of perfect symmetry versus broken symmetry is not just academic, it is fundamental. A perfectly uniform, isotropic web strongly supports our standard model of cosmology, where inflation erased all prior directional preferences, leaving behind a clean, democratic slate. But if these asymmetries are confirmed and not mere statistical flukes, they could be cracks in that model, windows into a deeper layer of reality. They might point to features from the universe before inflation, relics of a more chaotic birth that inflation could not completely smooth away. They could hint at exotic fields or forces that imprinted a direction onto the cosmos, a kind of cosmic grain like the texture of wood. This is why studying the geometry of the web for deviations from uniformity is a thrilling frontier. The web is not just a structure to be admired, it is the ultimate testing ground. By mapping the positions and motions of billions of galaxies with next-generation surveys, cosmologists are conducting a supreme audit of cosmic symmetry. They are asking, does the spacing of filaments obey the same statistical rules in every direction? Do voids grow at the same rate in all parts of the sky? Each subtle deviation from expectation is a clue, a potential message from the universe's first moments. This search challenges our most basic assumptions about the origin and structure of everything, pushing us to look for patterns within the pattern, a deeper geometry hidden within the grand design we have only begun to trace. The symmetry of the web holds secrets about the smallest particles in existence. To understand the finest brushstrokes in the cosmic design, we must consider its most ghostly inhabitants, neutrinos. These are among the most elusive particles known to physics, so insubstantial they can pass through a light year of solid lead without a single interaction. Trillions of them are streaming through your body every second, leaving no trace. In the early universe, they were even more abundant, a seething sea of nearly massless particles traveling at almost the speed of light. Yet, crucially, they are not completely massless. That tiny, almost negligible mass has a profound effect on the geometry of everything. Because these particles moved so incredibly fast in the hot, dense early cosmos, they behaved differently than dark matter. Dark matter, being slow and cold, clumped together readily under gravity. Neutrinos, however, were cosmic speedsters. Their high velocity meant they could easily stream out of small, growing gravitational wells, smoothing them over before they could fully collapse. Think of it like trying to build a sandcastle with a mixture of wet sand and dry, fine powder. The wet sand, like dark matter, sticks together and forms structures. The dry powder, like neutrinos, simply flows away, filling in the tiny crevices and preventing the finest, most delicate details from taking shape. This is what neutrinos did to the infant cosmic web. They acted as a form of cosmic sandpaper, erasing the smallest ripples in the density field. The consequence of this ghostly sanding is written into the universe's large-scale structure today. It preferentially suppressed the formation of the very smallest cosmic structures. We see this in a specific signature, a lack of granularity on the smallest scales. There are fewer tiny dark matter halos than our models would predict if neutrinos were truly massless. Correspondingly, we observe fewer faint, dwarf galaxies orbiting larger ones like our Milky Way. The web is not as finely detailed as it might have been, its smallest threads subtly smoothed away by a sea of particles that barely interact with anything. This gives cosmologists a breathtakingly indirect tool. By mapping the cosmic web with extreme precision and measuring exactly how clumpy matter is on different scales, from the vast filaments down to the faintest galactic satellites, scientists can infer the total mass of neutrinos. The degree of smoothing tells the tale. It turns the entire observable universe into a colossal particle physics detector. The architecture of galaxies and voids becomes a laboratory for measuring the properties of a particle that slips through our earthbound machines. This connection is profound. It links the impossibly large, the geometry of the cosmic web, directly to the impossibly small, the fundamental particles of the quantum world. The ghostly sand that smoothed the primordial canvas has left its faint signature in the grand design, a reminder that every scale of reality is woven together by the same underlying rules. Gravity may have drawn the blueprint, but the cosmic web is threaded with another, far more elusive kind of force. Woven through the vast filaments and empty voids are immense magnetic fields, invisible lines of power that add a subtle, complex layer to the universe's infrastructure. These are not the strong, concentrated fields of a star or a planet, but incredibly diffuse and ancient ones, stretching across millions of light years. Their strength is almost laughably faint, billions of times weaker than the magnet on your refrigerator, yet they permeate the largest structures in existence. They are the cosmic equivalent of a whisper that has traveled for eons, a whisper that can still guide the most energetic particles in the universe. The origin of these vast magnetic fields is one of cosmology's great puzzles. They were likely born in the turbulent infancy of galaxies and clusters, generated by dynamo processes as swirling plasmas of charged particles moved through seed fields that may have existed since the universe's earliest moments. Over billions of years, these fields were stretched and amplified by the same motions that shaped the web itself, spilling out from galaxies to fill the intergalactic highways. Today, they likely drape along the great filaments, tracing the same geometry that dark matter defined, and perhaps even tangling in strange configurations within the profound quiet of the voids. Detecting something so weak across such immense distances requires extraordinary ingenuity. Astronomers cannot simply point a telescope and see a magnetic field. Instead, they look for its fingerprint on light. As light from distant quasars or radio galaxies travels through the magnetized web, its polarization, the orientation of its waves, is gently rotated. By mapping how this polarization changes across the sky for thousands of sources, scientists can begin to chart the invisible magnetic landscape. Another clue comes from synchrotron emission, the faint radio glow produced when high-speed electrons spiral along magnetic field lines. A diffuse, hard-to-pin-down radio haze between galaxies could be the signature of these fields illuminating the web's bones. Understanding the geometry of these magnetic fields opens a new window into the cosmos's history. Do the field lines run neatly along the filaments like stripes on a cosmic ribbon, showing they were stretched and ordered by the large-scale flow of matter? Or are they chaotic and curled within the voids, suggesting different, more turbulent origins? The answer tells us about the thermal history of the intergalactic medium, the journeys of cosmic rays, and the energetic processes that have magnetized the universe beyond the islands of galaxies. It reveals a cosmos where not just mass but invisible forces of electromagnetism are woven into the grand design, a reminder that the universe's infrastructure is built from more than gravity alone. The cosmic web's magnificent connectivity is not its final state, but a temporary phase of cosmic youth. As dark energy's influence grows from a whisper to a roar, the very geometry of the universe will undergo a profound and lonely transformation. The acceleration of space itself will begin to pull the tapestry apart. Those grand filaments, the luminous highways connecting galactic cities, will not snap, but they will stretch. Over trillions of years, they will become thinner, more tenuous, as the expanding space between the galaxies within them grows faster than gravity can pull them together. The lifeblood of the web, the flow of pristine hydrogen gas along these corridors, will slow to a trickle and then cease entirely, starving future generations of stars. The galaxy clusters at the intersections will not vanish, but they will change. They will become isolated island universes, each one a brilliant, tightly bound metropolis surrounded by an ever-widening and permanent sea of darkness. The great migration of galaxies will end, not because they have reached their destination, but because the distances between destinations become mathematically impossible to cross. This leads to the most profound geometric shift of all, a change in what is observable. As the expansion accelerates, galaxies beyond our immediate gravitational neighborhood will eventually be carried away by the stretching of space so quickly that their light can no longer reach us. They will cross a boundary called the cosmological horizon, fading from view not because they have gone dark, but because the space between us is expanding faster than light can traverse it. Our observable universe, the portion of the web we can ever know, will shrink. the rich, sponge-like network we map today will, from our future perspective, appear to dissolve into a handful of nearby clusters adrift in an incomprehensible void. This long-term forecast, based on the relentless mathematics of dark energy, paints a poignant picture of cosmic destiny. It tells us that the intricate, interconnected geometry we are only now beginning to appreciate is a fleeting chapter. The web is a dynamic structure caught between its gravitational past, which wove it together, and its expansive future, which will pull it asunder. This realization adds a profound urgency to our current age of cosmic cartography. We are living in a privileged moment, a cosmic springtime where the connections are still visible and the architecture is still being traced by light. It urges us to look up and map the grand design in exquisite detail, to understand this brief, beautiful phase of connection in the long story of the cosmos, while the threads that bind it are still within our reach. But what if the very geometry we measure is telling us that our understanding of gravity itself is incomplete? The cosmic web may be testing the foundations of physics. For over a century, Einstein's theory of general relativity has been our master guide to the cosmos, describing gravity not as a force, but as the curvature of space-time itself. It predicts the cosmic web we see with stunning accuracy. Yet, a small but persistent question lingers in the minds of some physicists. Could there be more to the story? This is not about overturning Einstein, but about wondering if his magnificent theory might need a subtle extension when applied to the largest scales of the universe, where the fabric of reality is stretched to its limits. Alternative ideas have emerged. One prominent example is known as modified Newtonian dynamics, or MUND. This framework suggests that the effects we attribute to dark matter might instead be a modification of gravity's behavior in regions of extremely weak pull, like the outskirts of galaxies. Another possibility lies in theories that propose extra, hidden dimensions of space, which could subtly alter how gravity propagates across cosmic distances. These are not wild guesses, but mathematically rigorous attempts to solve cosmic puzzles, and each one makes a distinct prediction about the shape of reality. If an alternative theory of gravity is correct, it would leave a specific fingerprint on the cosmic web's architecture. Perhaps filaments would form with different thicknesses or connectivity. The statistics of voids, their shapes, and how empty they truly become might follow a different mathematical rule: the abundance of the most massive galaxy clusters, or the rate at which structures grow over cosmic time, could deviate from the standard model's predictions. This transforms the web from a beautiful structure into a precision instrument. By mapping its geometry with ever greater detail, cosmologists are conducting a supreme test. They are comparing the observed tapestry against the predictions of not just one theory, but many. Every precise measurement of a filament's density profile, every statistical catalog of void shapes, every count of galaxy clusters at a given mass becomes a data point in a grand experiment. A clear, persistent discrepancy between the observed web and the web predicted by general relativity with its dark matter and dark energy would be a revolutionary signal. It would be the smoking gun for new physics, a clue written in the language of voids and filaments that our current laws cannot decipher. So the quest to chart the cosmic web is about far more than making a map. It is about using the universe's own architecture as a laboratory, one of a scale and precision we could never build on Earth. The geometry we are tracing might be the very evidence that leads us to a deeper law of gravity, a new chapter in our understanding of how the cosmos truly holds itself together. The universe's grand design is not drawn in dark matter alone, but painted with a luminous, gaseous ink. While the dark matter skeleton defines the shape, it is the intergalactic medium, a diffuse and searingly hot gas, that fills the cosmic canvas and reveals its intricate brushstrokes. This is not the dense, cold gas within galaxies, but a far more tenuous substance that permeates the vast spaces between them, tracing every filament and clinging to the walls of every void. It is the universe's atmosphere, a wispy plasma so thin that a single cubic meter of it contains only a few atoms, yet it contains more ordinary matter than all the stars and galaxies combined. Its temperature is staggering, often reaching millions of degrees, heated by the shock waves of collapsing structures and the furious energy of ancient quasars. To map this ghostly, glowing fabric, astronomers use the universe's most distant lighthouses, quasars. These are the brilliant cores of ancient galaxies, powered by supermassive black holes whose light travels for billions of years to reach us. As that piercing beam journeys across the cosmos, it passes through the filaments and sheets of the intergalactic medium. Atoms within that gas, primarily hydrogen, absorb specific wavelengths of the quasar's light, leaving dark notches in its otherwise smooth spectrum. Because the universe is expanding, gas at different distances absorbs light that has been redshifted by different amounts. The result is a stunning pattern known as the Lyman alpha forest. Instead of a single absorption line, a quasar's spectrum shows a dense thicket of hundreds, even thousands, of these dark lines, each one a fingerprint from a different cloud or filament of hydrogen gas at a specific distance along the line of sight. This forest is not random undergrowth. It is a direct barcode of the cosmic web's gaseous structure. A dense cluster of absorption lines indicates the quasar's light has passed through a crowded filament where the gas is slightly thicker. A clearer stretch in the spectrum suggests the beam traveled through a more empty void. By analyzing the depth and width of each line, scientists can deduce the temperature, density, and even the motion of the gas that created it. A single quasar gives us a one-dimensional core sample, a narrow straw pushed through the cosmic foam. But by studying thousands of quasars scattered across the sky, astronomers can perform a grand reconstruction. They combine these millions of individual lines of sight, using sophisticated computer algorithms to stitch them together into a three-dimensional map of the intergalactic medium. It is a form of cosmic tomography, revealing the glowing gas that outlines the dark matter skeleton. This gaseous geometry tells a dynamic story of cosmic ecology. The filaments are not just static roads, they are active conduits. Cooler, denser strands of gas within these filaments flow steadily toward the waiting galaxies, providing the raw fuel for new generations of stars. This process, known as cold flow accretion, is how galaxies grow. But the story has another side. When stars explode as supernova, or when central black holes erupt in fury, they blast energy and metal-enriched material back out into the surrounding medium. This galactic feedback heats and stirs the gas, preventing it from cooling too quickly and regulating the growth of the galaxies themselves. The temperature and chemical composition of the intergalactic medium, read from the Lyman alpha forest, are a permanent record of this billions-year-long dialogue between galaxies and their environment. By reading this record, we complete our census of the universe's ordinary matter. For years, a significant fraction of the baryons predicted by theory seemed to be missing, unaccounted for in stars or the cool gas within galaxies. The hot, diffuse intergalactic medium, mapped through its absorption fingerprints, is where those missing baryons were hiding. They were not lost, simply woven into the faint, hot fabric of the web itself, a final piece of the puzzle that shows us the full, luminous form of the cosmic architecture. The orientation of a galaxy is not a random cosmic accident. Deep within the statistics of millions of galactic shapes, a subtle pattern emerges, a whisper that galaxies know their place in the grand architecture. Researchers have discovered that certain types of galaxies, particularly the smooth, football-shaped ellipticals, show a curious tendency to point their long axes along the very filaments they inhabit. It is as if each galaxy has a sense of direction, aligning itself with the invisible currents of the cosmic web. This is not a conscious choice, of course. but a fossilized imprint from the moment of its birth. The effect is incredibly subtle, visible only when you analyze vast numbers of galaxies across the sky, but its existence is a profound clue. It tells us that the web's influence extends far beyond simply gathering matter. It also spins that matter into a specific orientation. This alignment is a direct signature of the tidal forces exerted by the dark matter filament itself. As a proto-galaxy, a vast cloud of gas and dark matter begins to collapse billions of years ago, it does not exist in empty space. It is nestled within the gravitational landscape of a growing filament. The filament's immense mass creates a stretching force, a tidal field that gently tugs on the collapsing cloud. Think of it like shaping a ball of dough by pulling on its ends. The cloud responds by collapsing more readily along the direction of the stretch, the axis of the filament, while resisting collapse perpendicular to it. This process imprints a preferred orientation on the resulting galaxy, locking its long axis into alignment with the cosmic thread that birthed it. The galaxy's angular momentum, the direction of its spin, is also woven into this process, linked to the swirling motions of matter as it flows into the filamentary highway. Studying these galactic alignments provides a unique and powerful test for our theories of cosmic evolution. It connects the microscopic physics of galaxy formation directly to the macroscopic geometry of the universe. By measuring the strength and scale of these alignment signals in large galaxy surveys, scientists can probe the nature of the tidal fields that shaped them, which are dictated by the properties of dark matter itself. Different models of dark matter, such as warm dark matter versus cold dark matter, predict subtly different clustering on small scales, which would influence the strength and coherence of these tidal forces. If the alignments we observe match the predictions of our standard cold dark matter model, it is another point of confirmation. If they deviate, it could be a hint of new physics, a suggestion that the dark scaffolding of the cosmos has a different texture than we assumed. This realization adds a new layer of meaning to the cosmic web. It is not a passive stage upon which galaxies merely sit. It is an active sculptor that shapes them from the inside out. The web dictates not just where a galaxy will live, but the very axis around which it will turn. This subtle geometric fingerprint, written in the orientations of countless island universes, reminds us that every component of the cosmos is in dialogue with the whole, a connection preserved across billions of years. If galaxies carry this memory of their formation within their shape, what other subtle signatures might be hidden in their light, waiting to reveal the deeper forces that orchestrated this universal design? Our universe's unique geometry might be a local signature. The precise spacing of filaments, the delicate balance between clusters and voids, the very rules that gave rise to this grand design, could be a single expression of physics within a much vaster and stranger landscape. This leads us to the most speculative frontier in cosmology, the concept of the multiverse. In theories like eternal inflation, our Big Bang was not a singular, unique beginning, but the nucleation of one bubble in an endless, frothing sea of spacetime. In this picture, new universes are constantly budding off from an eternally inflating background, each one a separate bubble with its own random set of fundamental constants and physical laws. Imagine a cosmic foam where each bubble is an entire universe, potentially as vast and complex as our own, but governed by entirely different rules. In such a landscape, the architecture of cosmic webs would not be a universal truth, but a local artifact. The specific outcome we see, the beautiful sponge-like pattern of filaments and voids, depends critically on the numbers that define our reality. The strength of gravity, the amount of dark matter, the push of dark energy, the initial quantum fluctuations from inflation, all of these are dials that were set, perhaps randomly, when our particular bubble formed. Turn those dials to different values, and the resulting cosmic geometry could be unrecognizable. In a universe where gravity is much stronger or dark matter more abundant, matter might collapse into a single, monstrous supercluster almost immediately, leaving no room for a delicate web of filaments. In another universe where dark energy dominates from the start, expansion might be so violent that no structures form at all, resulting in a vast, featureless emptiness, a cosmos of pure void. There could be universes where the cosmic web is far more intricate, a dense lacework of filaments with no empty spaces, or ones where matter is arranged in vast, crystalline sheets instead of threads. While these ideas are currently beyond the reach of direct observational test, they serve a profound philosophical purpose. They challenge the assumption that our universe's geometry is inevitable. The specific pattern we have spent this journey mapping, the grand design that feels so fundamental to reality, might be just one possibility in an infinite ensemble. This shifts our perspective from discovering universal laws to characterizing a single, possibly unique cosmic habitat. It invites a humbling thought. The geometry we study with such care is not merely the output of impersonal physics. It is the signature of our home, the spacing of galaxy clusters, the prevalence of voids, the very fact that a complex web could arise at all. These are the characteristics that allowed galaxies, stars, planets, and ultimately, observers like us to emerge. In this light, our meticulous cartography of the cosmic web becomes more than science. It becomes a form of cosmic self-discovery. We are not just mapping the universe, we are reading the unique architectural blueprint of the bubble we happen to inhabit, a blueprint that made our own existence possible. The vast architecture of the cosmos is being mapped by an army of explorers, many of whom have never set foot in an observatory. This is the world of citizen science, where the monumental task of charting the cosmic web is open to anyone with curiosity and an internet connection. Projects like Galaxies pioneered this approach, inviting hundreds of thousands of volunteers to do something computers still struggle with, to simply look. By classifying millions of galaxy shapes from survey images, these public cartographers have helped scientists understand a fundamental link: how a galaxy's form and behavior are influenced by its address within the web's filaments, clusters, and voids. Each click contributes a data point, revealing whether a galaxy lives in a dense urban cluster or an isolated filamentary highway, patterns essential for testing our models of cosmic evolution. Newer initiatives are taking this public partnership even deeper into the geometry itself. Imagine logging into a platform and being presented with a three-dimensional map of the local universe, a pointillist artwork of millions of galactic positions. Your task is not to classify a single object but to trace the connections. You might be asked to identify the faint, diffuse boundaries of a cosmic void, or to help flag the tentative lines where a filament of galaxies appears to bridge two massive clusters. This work requires a human eye for pattern and context, an intuitive grasp of structure that even sophisticated algorithms can miss. By participating, individuals become direct contributors to the greatest map ever made. They are not just learning about the cosmic web, they are helping to trace its invisible lines, becoming cartographers of reality on the grandest scale. This collective effort transforms cosmic discovery from a remote, academic pursuit into a shared human endeavor. It blends the immense processing power of public curiosity with advanced computation, accelerating research in ways no single team could achieve. Every classification, every traced filament, adds to our collective understanding of the universe's hidden architecture. This democratization of exploration makes a profound point that deciphering the geometry of the cosmos is a journey we are all on together, each participant helping to illuminate a small part of the grand design that connects everything. This hidden architecture of the cosmos speaks a universal language of beauty. Beyond the data and simulations, the geometry of the cosmic web has ignited a parallel exploration in the realm of art, where filaments and voids are translated into stunning visual and physical forms. These creations are far more than mere illustrations. They are profound interpretations that make the invisible architecture of our universe feel immediate and tangible. Digital visualizations from supercomputer simulations often resemble vast, glowing neural networks or intricate root systems, forms that feel eerily familiar because they echo patterns found throughout nature. This resonance is no accident. It reflects the universal mathematical principles that govern growth and connection, from the branching of trees to the firing pathways of our own brains. Artists captivated by this cosmic structure have rendered it in sculpture, using twisting metal and light to evoke the curvature of filaments, and in painting, with washes of color suggesting the deep, empty gradients of voids. These works do not simply depict, they invite an emotional and intuitive understanding of scale and connection that raw data alone cannot convey. The collaboration between scientist and artist is crucial here. Researchers provide the precise maps and data, the true coordinates of the cosmic landscape. The artist then interprets this framework, exploring color, texture, and form to communicate the awe, the grandeur, and the profound mystery of the structure. This partnership ensures the art remains rooted in scientific reality while reaching for something more, a felt sense of our place within this immense design. When you stand before a large-scale installation of the cosmic web, you are not just looking at a model, you are momentarily immersed in it, surrounded by the idea of these impossible connections. This fusion of disciplines reminds us that our quest to understand the universe is a holistic human endeavor. It requires the rigorous logic of mathematics and the boundless creativity of the artistic mind. One seeks to explain the mechanics, the other to express the meaning. The cosmic web, in its perfect balance of order and emptiness, serves as an ideal muse, a structure whose scientific truth is inseparable from its aesthetic power. It bridges the cold vastness of space with the warmth of human perception, allowing us to appreciate the architecture of all things not just as a fact, but as a form of sublime art. This artistic dialogue enriches our cultural relationship with the cosmos, transforming abstract geometry into a shared experience of wonder. The true map of the cosmos is still being drawn, and the next generation of explorers are not ships but telescopes of unimaginable power. These instruments, now under construction or soon to launch, are designed not just to see farther, but to see the hidden geometry of the universe with a clarity we have only dreamed of. They will transform our two-dimensional sketches of the cosmic web into a living, breathing, three-dimensional atlas, charting its evolution across nearly the entire history of time. The Vera C. Rubin Observatory, perched on a mountaintop in Chile, will conduct a 10-year cinematic survey of the sky called the Legacy Survey of Space and Time. Its enormous mirror and giant digital camera will capture the entire visible southern sky every few nights, imaging billions of galaxies and detecting subtle changes. This will give us an unprecedented two-dimensional map of the web's luminous skeleton, but with such depth and statistical power that we can infer the third dimension through the subtle distortions of gravitational lensing, seeing the dark matter framework in exquisite detail. While Rubin scans the visible sky from the ground, the Nancy Grace Roman Space Telescope will peer into the infrared from its orbit around the Sun. Infrared light slips through cosmic dust that blocks visible wavelengths, allowing Roman to see the earliest, most distant structures in the universe with stunning clarity. It will look back to an era when the cosmic web was first assembling, capturing the infant filaments and protoclusters as they were just beginning to condense from the primordial fog. This is like comparing a photograph of a finished cathedral to blueprints of its foundation, allowing us to trace the web's growth from its earliest moments to the present day. Yet to understand the web fully, we must map not just the galaxies but the invisible gas that flows between them. This is the mission of the Square Kilometre Array, a revolutionary radio telescope being built across 2 continents. The SKA will not see light, but will detect the faint radio signature of neutral hydrogen gas, the primary fuel of the cosmos. Because this hydrogen is everywhere, the SKA can create a true 3-dimensional tomographic scan of the universe, tracing the web's gaseous filaments and voids across billions of light years and billions of years of time. It will show us the rivers of raw material flowing into galaxies and the vast, empty chambers expanding between them. Together, this triad of next-generation observatories will measure the cosmic web's geometry with a precision that will test our fundamental models to their breaking point. They will measure the exact rate at which filaments thicken and voids expand, providing the most stringent test yet for dark energy's relentless push. They will count the faintest dwarf galaxies and map the smallest dark matter clumps, probing the nature of the invisible particle that built the cosmic skeleton. Perhaps most excitingly, they may discover entirely new classes of structures, patterns in the architecture we have not yet predicted. The universe has surprised us before, and with instruments of this power, we are almost certain to find something unexpected, a kink in a filament, a peculiar alignment of voids, or a flow of galaxies that defies our current gravitational understanding. These potential anomalies are not failures of our theories, but gateways. Each one could be the clue that leads us to a deeper law, a refinement of gravity, or a new understanding of the dark components that shape our reality. We are on the verge of moving from simply admiring the grand design to interrogating it, asking the universe to reveal the deepest secrets of its construction, written in the geometry of everything. This intricate architecture we have mapped, from the quantum whisper to the galactic supercluster, compels a question that lies beyond the reach of any telescope. Does the universe's profound geometry reveal a cosmos of cold, indifferent machinery, or does it whisper of a deeper, inherent order waiting to be understood? The very fact that we can trace this design, that the human mind can formulate mathematics that predict the spacing of filaments billions of light years away, is itself a staggering revelation. It suggests a universe that is, at least in part, knowable. We have found the rulebook written in the language of physics and geometry, and we are slowly learning to read it. This comprehensibility is a gift, a strange resonance between the logic of our minds and the logic of the cosmos. Yet this same map delivers a humbling dose of perspective. Our entire world, every human life and all of recorded history, unfolds on a speck of rock orbiting an unremarkable star. That star is one of hundreds of billions in a galaxy that itself resides on the quiet outskirts of a filament, a suburban lane in the vast metropolitan sprawl of Laniakea. And this entire magnificent web, with all its clusters and voids, may be just one bubble in an infinite froth of universes, each with its own unique set of physical laws and perhaps its own alien geometry. This dual realization is where science meets philosophy. In terms of sheer physical scale, our presence is vanishingly small, a transient flicker in an arena of incomprehensible size and age. We are, by any cosmic measure, insignificant, but significance is not solely a function of size. Our consciousness, our curiosity, our drive to understand, transforms our place in this narrative. We are the universe becoming aware of itself. The particles that form our bodies were forged in the hearts of ancient stars and woven into the fabric of the cosmic web. Now those same particles have arranged themselves into a pattern complex enough to look back, to trace the filaments of its own origin, and to wonder why. This ability to perceive and question the grand design is a kind of cosmic significance that transcends physical dimension. The hidden geometry thus challenges our most ancient questions about place and purpose. Are we merely accidental passengers on a random filament? Or is the fact that a universe can produce beings capable of understanding its own structure a meaningful feature of that structure itself? The web shows us that everything is connected, from the largest supercluster to the cells in our bodies, by a shared history and a common set of physical laws. This interconnectedness does not dictate a purpose, but it redefines isolation. We are not separate from the cosmos, we are a dynamic, thinking expression of it. Our fate is tied to the geometry as our galaxy continues its slow journey along the filamentary flow. Our understanding grows from it as each new map reveals more of the rules. To contemplate this is to stand at the intersection of awe and inquiry, feeling both profoundly small and uniquely privileged to be witnesses to such a beautifully structured reality. This synthesis reveals a cosmos built on elegant, universal principles, a handful of simple rules written into the fabric of reality at its birth, have unfolded over billions of years to create the breathtaking complexity we observe. It is a story of emergence where immense structure arises from minimal ingredients. Those initial quantum seeds, nearly imperceptible ripples, contained the entire potential for the cosmic web. Gravity, acting as a relentless amplifier, turned those whispers into the deep gravitational wells of clusters and the sweeping slopes of filaments. Dark energy, the counterforce, now stretches the canvas upon which this design is drawn, determining its ultimate scale and fate. Every component plays its part in this geometric symphony. Dark matter provides the invisible framework, the bass note of gravity that holds everything together. Ordinary matter, the baryons, flows like a luminous melody along that framework, condensing into the bright points we call galaxies. Neutrinos, those ghostly particles, sand away the finest details, subtly smoothing the smallest scales. Even magnetic fields, faint as they are, trace their own delicate lines through the vastness, adding a layer of invisible texture. This is not a chaotic assembly, but a coherent structure where each piece fits. The dense clusters and profound voids are two sides of the same coin, one defined by the absence of the other. The filaments are not random scribbles, but the most efficient gravitational paths matter could take as it flowed toward the growing nodes. The statistical symmetry we see on the largest scales is the direct echo of the uniform conditions set by inflation, while the potential anomalies, the hints of bulk flows or alignments, are the tantalizing clues that our map may still be incomplete. To hold this entire narrative in mind is to grasp one of the great triumphs of the scientific endeavor. We have connected the realm of the unimaginably small, quantum physics, with the domain of the impossibly large, the cosmos itself. We use mathematics, a language of pure logic, to describe the history of everything, and we confirm those descriptions with painstaking observations that span the electromagnetic spectrum. This geometric understanding transforms the universe from a collection of mysterious objects into a single, evolving entity. The cosmic web is a dynamic fingerprint, its unique pattern encoding a record of the past, a snapshot of the present, and a forecast of the future. It tells us what the universe is made of, how it has changed, and where it is going. To decipher this geometry is to read the autobiography of the cosmos, written not in words but in the precise arrangement of galaxies and the vast, silent spaces between them. This grand synthesis, however, leads to a final, reflective question. If we can read this cosmic story, what does it tell us not just about the universe, but about our own place within its magnificent geometric design? This hidden geometry is far more than a beautiful pattern. It is a master key, a cosmic diagnostic tool that allows us to interrogate the universe's deepest secrets. By measuring the precise spacing of filaments, the growth of voids, and the clustering of galaxies, we are not just mapping a static structure, we are taking the universe's vital signs. We can weigh the ghostly neutrino, measure the push of dark energy, and stress test the very laws of gravity, all by observing how this grand architecture has been stretched and woven over time. The cosmic web is the ultimate experimental result, a data set written across the sky, waiting for us to learn its language. Our journey has taken us from the faintest quantum whisper in the first instant to the luminous superclusters of today, all connected by an unbroken thread of cause and geometric effect. This continuity is the great triumph of cosmology, revealing a cosmos that is coherent, lawful, and astonishingly comprehensible. We now stand at a threshold, with next-generation telescopes poised to scan this architecture with unprecedented clarity. Every new map, every traced filament and measured void, is a step toward a more complete understanding. It brings into sharper focus not only the universe's history, but our own place within its vast, interconnected network. To gaze upon the cosmic web is to witness a universe that is profoundly structured, yet filled with enduring mystery. Its geometry is a silent, majestic proof that we live in a cosmos that can be known, explored, and forever wondered at. If this exploration of cosmic architecture has reshaped how you see the night sky, consider joining us for more journeys into the universe's deepest questions. We would love to hear what part of this grand design resonates most with you. What aspect of the cosmic web's hidden geometry leaves you in awe? Share your perspective in the comments below.